Hey everyone, and welcome to today's Explainer. Today, we're looking at something incredibly cool, the Janus membrane, which is a genuinely sustainable solution to air pollution. It's this fascinating look at how scientists are essentially borrowing a page right out of nature's playbook to solve one of the most stubborn environmental problems we're facing today.
Okay, let's dive right into this. We're going to start with a question. How exactly do we destroy toxic air pollutants that just refuse to mix with water? I mean, it sounds like a strange riddle, right? But this is actually a core scientific paradox, and it's a microscopic battle that has massive, real-world implications for all of us.
To really understand why solving this riddle matters so much, we need to ground ourselves in the stakes. Every single year, just in France alone, air pollution is responsible for tens of thousands of deaths. Tens of thousands! The scale of the problem is just monumental. We're talking about an ongoing, silent crisis happening right now that affects millions of people.
Now, when we picture air pollution, our minds usually jump straight to those massive factory emissions, right? Thick smoke, visible smog blocking out the sun. Visually, that anchors the threat for us. But the reality is actually a lot sneakier. The absolute most dangerous parts of this pollution are the completely invisible molecules hiding inside those clouds. Those are the specific targets we desperately need to neutralize.
And those invisible threats have a name. We call them VOCs, or Volatile Organic Compounds. These are the main antagonists of our story today. VOCs are highly toxic molecules. We're talking about things like hydrocarbons, alcohols, and aldehydes. They volatilize, which basically just means they evaporate super easily, and then they persist in the atmosphere. But what makes them so profoundly dangerous is their ability to spread, not just outdoors, but right inside the confined indoor spaces where we live and work every day.
Now, it's not like we're completely defenseless here. We do have ways to fight VOCs right now. Methods like thermal oxidation, adsorption, and condensation have actually been used for a while. But, well, these traditional methods are severely limited. They run into major roadblocks when it comes to high costs, a general lack of efficiency, and sometimes they even carry their own negative environmental impacts. So the takeaway, relying entirely on them just isn't a sustainable long-term solution.
Which brings us to a highly promising natural alternative. Enter our biological heroes, the enzymes. Instead of relying on harsh, energy-intensive chemistry, scientists are turning to nature's microscopic Pac-Man. Enzymes possess this incredible specialized ability to selectively transform and literally destroy specific pollutants. It's like nature has already engineered the ultimate cleanup crew for us.
But of course, there's a catch. We run into what we can call the hero's dilemma. Think of it as the ultimate oil and water analogy. So the crucial point here is that many of these dangerous VOCs are completely hydrophobic. That means they hate water and they dissolve very poorly in it. But our hero enzymes, they are hydrophilic. They absolutely love water. In fact, they literally need water to remain active and survive. So if you can't get the pollutant and the enzyme into the same room together, the enzymes can't do their job. It's the ultimate microscopic standoff.
To bridge this seemingly impossible gap, researchers in France and the United Arab Emirates came up with a brilliant workaround. They engineered a solution called the Janus enzymatic membrane contactor reactor. I know, it's a bit of a mouthful, but it actually takes its name from Janus, the Roman god with two faces. And that's because it literally acts as a two-faced interface between two completely unmixable worlds.
And this brilliantly illustrates how this microscopic magic trick works in practice. First, the VOCs are transferred from the air into an organic liquid phase, an environment they actually like and have an affinity for. Step 2, the pollutants pass through the membrane's water-hating hydrophobic layer. And then step 3, waiting right on the other side, tethered to the water-loving hydrophilic side, are our enzymes. The pollutants diffuse across, and bam, the enzymes destroy them. The pure genius of this system is that it allows the two sides to interact without the organic and water phases ever physically mixing.
If we zoom in on the specific materials of this border checkpoint, we find two highly specialized layers. The hydrophobic layer, the one facing the organic phase with the pollutants, is made of polyvinylidene fluoride. And bound tightly to it is the hydrophilic layer made of cellulose acetate, which is where the enzymes are grafted. Maintaining strict separation between the two liquids while simultaneously allowing the pollutants to diffuse across, well, that's the absolutely essential condition that guarantees this whole device actually works.
So, you might be wondering, does this elegant theory actually work in practice? The hard data says yes, absolutely. When the research team tested this system on phenol, which is a very common standard model pollutant, the results were fantastic. This enzymatic membrane eliminated up to 74% of the toxins in a span of just 10 hours. 74%?
But the impact of this breakthrough, it goes way beyond just raw efficiency. It's really about longevity. As the researchers point out, the enzymes immobilized on the membrane can be reused over several cycles, which considerably improves the sustainability of the process. And that is exactly why this matters for our future. We aren't just destroying pollutants, we're doing it with a highly reusable, environmentally sustainable biological tool. It's a total game changer.
Which leaves us with this final, remarkable thought. If we can literally force oil and water to cooperate at the microscopic level just to clean the toxic air we breathe, what other impossible chemical divides can we bridge to save our planet? The success of the Janus membrane proves that sometimes the solutions to our biggest environmental threats are hiding right there in the smallest biological interactions. Thank you so much for joining me for this explainer, and as always, stay curious.